Hello everyone. This lecture focuses on reviewing basic statistical concepts relevant for power and sample size analysis. We focus on concepts and logic behind statistics, and we do not emphasize statistical symbols or equations. This brief lecture is a review of the key ideas we will reference in later lectures. The learning objectives cover the logical basis of scientific research, which generally aims to test hypotheses. We will examine related concepts such as probability functions, power, and factors that influence power. The goal of most scientific research is to test hypotheses. Hypotheses for us are testable theories about how the world works. There are many questions we can address in this manner, such as, what is the association between maternal fat intake and infant outcomes? How well do we know whether an alcohol prevention program reduces drinking? How do we know whether an educational program influences student achievement? The key here is that we seek to examine the relationship between two or more events. To formulate a hypothesis, we must first state the null hypothesis, which is the claim there is no relationship between two or more events. We use statistics as a tool for evaluating these hypotheses. Statistics allow us to evaluate the chance that the null hypothesis is in fact true, given the observed data. A main focus in this course is understanding the statistical concept of power. For us, power is the probability of rejecting a null hypothesis. Generally speaking, our scientific goal is to reject the null hypothesis, so power is a very important concept as it relates to hypothesis testing. In a study design, power is used to calculate how many participants should be included in a study. With a target power in hand, we can figure out how big the sample size should be to achieve a given target. As we will discuss later in the course, a study with a sample size that is larger than required may needlessly endanger research participants. A study with a sample size that is too small may fail to reach the scientific goals, thus putting research participants in danger for no benefit. Power and sample size is a major ethical consideration. Scientific research depends on the calculation of probabilities. We calculate probabilities, or p-values, by using things called cumulative distribution functions. These are equations used to calculate the probability of an outcome for given values of independent variables. You can see examples of this shown on the screen, with an associated probability. Many random variables are continuous and have density functions, which are used to compute cumulative distribution functions and in turn probabilities of interest. This kind of inner workings is how we compute p-values. When graphed, probability density functions take on highly characteristic shapes. Here's a familiar shape, the normal distribution or normal density function. One of the ones that we will use a lot in this course, because we're doing multi-level and longitudinal studies, is called the central F distribution. It forms a skewed shape. Keep in mind, these are just pictures of the functions, and we use these pictures to calculate p-values when we're doing hypothesis testing. Probability is calculated by finding the area under the curve of a probability density function. The area is the probability that the test statistic is more extreme than the observed statistic. For our current data, we can compute an F statistic. On the graph shown on the slide, the F marks the location of the observed test statistic. The p-value is the chance that we would observe the data that were more extreme if in fact the null hypothesis is true. It is an area under the curve that is to the right of the observed statistic. It is the probability of observing F statistics larger than that seen in the current data. The area under the curve is called the p-value. Small p-values are the holy grail. If you can get a small p-value, you can reject the null hypothesis, then you can achieve your scientific goals and provide better outcomes for your target population. A type 1 error occurs when the statistical test mistakenly rejects the null hypothesis when it in fact is true. We can only trust findings if several studies arrive at the same conclusion. What we hope for is replicated findings. We want to show something in our study, and we want our colleagues across the country and world to find the same thing. It's only by seeing many studies that achieve the same thing that we start to believe the things are true. Scientific knowledge grows from the steady accretion of replicated studies. The goal of science is to be both public and replicable. Outside of scientific studies, we often believe two things are related. For instance, we might think that if a child drops maple syrup on the floor may become sticky. In science, we usually go backwards. A null hypothesis claims that two events are not related. In this course, we're going to focus on hypotheses about average responses from different groups. Average responses for two groups, here intuitively labeled equal and different, are either the same or different. These average responses could be on virtually any measures like educational achievement or health outcomes. As a reminder, our goal here is to reject the null hypothesis, and power, which is the subject of this course, is the probability of rejecting that null hypothesis. If we achieve an appropriately high power, such as 0.9, it's going to give us confidence about the accuracy of the study's conclusions. In fact, it will give me even more confidence that the study will actually be able to achieve its goals. Power depends on a number of different things, such as the sample size of the study. However, there are less obvious factors that matter as well. For instance, power also depends on the strength of the relationship between two events. Some relationships are easy to see, like the relationship between smoking and lung cancer. Some things are very hard to see. The strength of relationships here matter. The degree of variability in the system also makes a strong difference. The degree of variability measures the spread of these data. Power also depends on statistical tests, which we'll talk about some more later in this course. Finally, note power also depends on the type 1 error rate. Let's review what we've learned in this lecture. We use hypotheses to describe relationships between events that occur. Then we conduct research which either allows us to either reject the hypotheses that were made or fail to reject them. Throughout this course, you will often hear us refer to the null hypothesis. This says that there is no relationship between two or more events that we are exploring. As scientists and researchers, we often claim that we're aiming to reject the null hypothesis, meaning there is some association or relationship between the two events we did not know about before. Finally, this course is all about power, the probability of rejecting the null hypothesis. Since rejecting the null is our goal, we do want to do all that we can to keep our power as high as possible. Throughout this course, we are going to talk about various ways to do this. That's all for this lecture. Thank you so much.